and switch this to that. Good. So variables is not the right project. During the last lecture, we already started with flow control, as just mentioned, and today we will continue with that. So during the last time, we had just the very beginnings of flow control. So we had ifs and else ifs and switches, which are the most basic things that you can have with regard to controlling what your application does. Basically, you can make things conditional, and as we might remember, we have seen already some sort of conditional code execution already when doing variables and their logical operators, which instead of working in a mathematical way, actually already changed very slightly the flow of the program execution, directing it either to a set 1 or to a set 0, or to more complex expressions if we use the trinary operator. And now the next thing which is quite useful to learn is how we can create loops. So I already told the last time that next thing on the agenda will be loops. So let's do that. A loop is a very simple flow control structure. It is just a code snippet which repeats itself until some break condition is met. In certain scenarios, you can also use endless loops, meaning there is no break condition. Usually, of course, those situations are rather rare because usually you want at least at some point when you end your program to have a break condition, but a very prominent case where you really don't is, for example, when you are writing programs for an Arduino or for any other microcontroller. Generally, the way this is done is that in the main function of your program, you have a endless loop which then just repeats itself endlessly and until you unplug the power from your microcontroller, basically. And at this level, of course, if you write some very low-level code, then you might also find situations where you want to something be done in a loop and never terminate. In desktop applications, this is rather uncustomary, although what you of course can do is you don't care for the exit behavior and just have an endless loop until the program gets killed. But this, as said, is not a good practice, so you should always, when writing for a desktop application, consider some graceful shutdown scenarios. Also, when doing loops which might run for a longer period of time, it is good practice to offer the user ways to, first of all, some sort of feedback what the loop is doing, or at least how long it will be doing it, as well as maybe some way of gracefully terminating the execution without discarding all that already have been done. But these are more advanced details, so for now let's just see how such loops in C and C++ can be made. And in fact there are three types of loops. The first one is the simple for loop. Just start with the keyword for, then you open brackets, and then you have three sections which are separated by semicolons. And after the for loop, like with the if, you can have some code block. It can be a single line, or it can be multiple lines enclosed in a set of curly brackets. So this defines as a code block. And the way this works is the first block here in the loop is only executed once when the loop starts. So for example, we could assign a value to a variable. We can also define a variable. So for example, int e is equal 0. This will be done once and never again. The next is a condition. The condition is a code block which is executed each time before the loop body. So whatever comes here, even if it's just one line, gets executed. And this condition must be true, else the loop will break and the loop body will no longer be executed. So in this case, you have a way to test even for the first case. So a loop is not this sort of loop is not guaranteed to execute even once. It really depends on the condition. So here let's go with something very simple. Let's say I is less than 10. So we want to execute the loop as long as I is less than 10, and if we don't do anything else, this loop would still run forever because there is nothing that would change I. So the next block here is executed after the code block is finished. So the for loop does something, this code block is done, and then the execution flow goes here, and then you can, for example, make I++, i.e. we increment I by 1. And once this code block is done, then the whole thing starts again at checking the condition, executing the code, the main body, jumping to the third code block, checking the condition, executing the body, jumping to the code block, checking the condition, and at some point the condition will no longer be true, at which point it jumps to the first address after the loop, whatever that might be. So let's maybe add a helper variable. Int my counter is 0. Let's also increment this counter here, or we could actually maybe start with 1 and then just multiply it by 2 each time, or we could also multiply it by itself each time, whatever, doesn't really matter. The thing is that we just do something, and then of course at some point we would want to either return the value or use it for something, or just overwrite it if we don't care for the result, and then do, for example, the next loop. But before we go to the next sort of loops, let's quickly take a look here how this looks in the assembly. So we put a breakpoint at the very first instruction we might be interested in, or even before that. We run the program, and once everything is done loading, I guess we had an update since the debugger's redownloading symbols for standard libraries. So each time Windows updates and the files change, your debugger will need to download new debug symbols for the Windows libraries which are used by your application. Okay, so we are here. So we see, of course, we have one line here, or rather an opcode here, which represents this line and just assigns 1 to our counter. And then we have the whole loop. So let's step through it. First, we are assigning 0 to some memory region. That will be our I variable, most likely. Then we have a jump. So this jump is unconditional, so it's always taken. Then we have here our comparison. So we are comparing now whether I is less than 10, which apparently it is, since it's 0. Then we have a conditional jump, which in this case is not taken. So the condition is met for this in the sense that we want to execute the loop body. Then we do it. Basically here we just load the value, shift left, so it optimized the multiplication with a trick. Instead of multiplying by 2, it is shifting all the bits by 1 to the left, which has the exact same effect on a integer number, but is much more efficient and faster to execute. It even did this in our debug build. So very old compilers would always do exactly what you tell them, and then of course it would be reasonable in such scenarios to try to optimize yourself by using a shift operator instead of a multiplication. But modern compilers are smart enough that they do it always even in a debug build, and meaning such tricks are not needed, and it is probably better to write more readable code using the multiply operator, as it will still be as efficient as if you would use some more obscure method to save some clock cycles. Okay, so we have here a shift left, then we write the value back to the variable, and then we have a unconditional jump back to the beginning. Now we are arriving here. This place, as you might remember, we have jumped over. This is the code block which does the incrementation. So again, we reload the value of I into a register, we increment it by 1, we store it, and then we naturally arrive at the next instruction to which we jumped before over jumping this block, the compare instruction, and from this point on out, the whole execution is already as we had. Then the whole thing will repeat and repeat and repeat and repeat and repeat until at some point this jump will be taken, and then we will end up, let's see how where are we now. We are at 3 hours. That will take forever. So let's just put a breakpoint here and jump to it. So we haven't seen it, but it kind of would be boring to just go through the loop 10 times. Actually, I could just make the loop go two times. That would also be a trick. But basically, what happened is that here this jump, if greater equal, was taken, and then we just jumped out of the loop. And then we have the end of our function. Okay, so let's remove those breakpoints. And we can also maybe slightly modify it. We can use like ×3. You cannot do ×3 with the shift operator, and also we can make the loop just go twice, so that we can really see how these things are taken. So here, so again we start. We jump over the increment section directly to the comparison. The comparison says we can go, and now you see it uses the integer multiply opcode, which is on modern CPUs it's very fast still. On very old CPUs it might be like hundreds of times slower than a bit shift, especially on microcontrollers and things where you really have to save on silicon space, on cheap stuff basically. But at least it saves a few picowatts if you do it more efficiently, so it's good that the compiler tries to optimize wherever it can. This also, I think, illustrates really nicely that the code which you might get from a modern compiler really might not be what you wrote in your code or expect. It will be functional. It functionally will be doing what you tell it to do, but the way it achieves this might be very far away from a straightforward approach what one would think, especially if you would have a release built with really a lot of optimizations turned on. Okay, so we repeat this. We go here, we increment, we check, we do it the second time, and when we now try to do it the third time, we will break out of the loop, because now the value I was 2, and then of course the condition was no longer met. Good. So let's leave this at this, and let's see about what other types of loops we can have in C++. The next one is a while loop, and basically really in like almost all cases you only need the for loop. Why historically there are 2 more loop types is well, a question for a historian. I don't know the answer. I know that the third loop type I will show you has a special use case which kind of justifies its existence, but the while loop, which you write like while opening and closing brackets, and then you have just a condition. Let's say counter is less than 3, and then you have your body and nothing else. You don't have initialization, you don't have increment, so you need to do your own initialization, you need to do your own incrementation, but what you can do basically is you can just write for, and this is exactly the same thing. It will generate the same code. Why you have the ability, how does it look best? It looks best like this. Why you have the ability to have a while and a for loop? Maybe because other languages had multiple loop types, and when they designed it, they decided that they also want more than one loop. I don't know. I know Visual Basic, for example, has also an until loop, which is basically like a while just with a built-in negation, which you don't have in C++, luckily, because it would be unneeded. The other one, which is kind of not redundant, is the do while loop. And the thing that makes it special is that you start with do, and you don't write anything but your code block, and then you write while and the condition. And this loop, the way it is set up, is made that it will always execute its body at least once. So the condition, the while condition, let's copy the same one from here, will only be evaluated once the whole loop executed. So you have the guarantee that it will at least do something, at least once, and that might be useful. I'm not using those types of loops very often, but you might find them useful in special cases. So I guess it's nice that they added this. More modern languages usually just have a for loop and nothing else. Although that said, once we go to C++ and more modern C++ features, we will see also a so-called ranged loop, which also starts with a for, but it allows you to iterate through multiple entries in an array or in a container of sorts. But this is, as said, a more advanced feature, and for now, since we are starting only with the basics, we are silently ignoring that. Other languages also implement such loops. They usually call it a for each loop, because the idea is that if you have something that contains multiple elements, you're using this loop to iterate through all of them, which is kind of useful. And what we are in fact could do is even in C++ using preprocessor definitions and some own container types, you could create your own for each loop keyword. And in fact, the Qt framework, which we will take a look on during part 2 in the next semester of this course, in fact implements such a custom for each loop type, which technically in C does not exist. Which is quite nice, as it's very convenient. Now, having these loops, of course, is nice, but what else, of course, would be even nicer is if we could control the execution to a finer degree. And in fact, we can. So when we have our loop, we can use the break keyword to break the execution, meaning that as soon as something happens and the break is invoked, then the loop will jump out of the loop, no matter how many iterations might be left. So for example, if we change this back to 10, then and here let's say if my counter is greater than 10, and if we multiply by 3 each time, it will be quite quickly the case. Then break. So in this case, this end condition will never be triggered. In this very simple code, which we are looking on here, of course, this kind of appears not needed. But of course, if you will have more complex code where you are, for example, reading from a file or computing something, being able to break the loop at any point is quite convenient. Of course, you could have some sort of workaround, which I will show in a second. But for now, let's just see what this will do and how it works. So again, we start here, we do the comparison, this here. We did not take the branch to the break, so we arrived at this jump, which is at the end of the loop, which brings us back to the beginning. Then we increment, check, don't break out of the condition for now. Here, repeat the thing, then we have our if. Then this was still fine. I guess we have 9 currently, and then if we repeat this one more time, this condition will this time bring us to the jump instruction. As you see here, it's basically the same instruction, just slightly further down, and it jumps from here, from this address, directly to this address, i.e. to the next thing, whatever is after the loop, breaking out of the loop effectively. So this is the break keyword. You can use this break keyword in any other loop type. So this is standard. Important to know is that if you have multiple loops, break only breaks out from the latest one. It doesn't break out like if you have nested loops, a loop in a loop, loopy loop. For and e, oops, like null, e less than 3, e plus plus. Then repeat the same thing with j. J plus plus, and then break. If we run this, we will see it will only break us out of the inner loop, but the outer loop will stay unaffected. And so here, okay, so we entered the loop, we will do the break, and we entered, and we repeat the outer loop still, however many times, 3 times, we have told it to repeat. Breaking out of more than one loop at a time is challenging. Well, challenging. it's relative. It's not as trivial as all the other things which we have learned until now. Let's say it like this. And there are a few ways how we can do it. One way, the pedagogically more correct way, let's say, because it is kind of much more safe, is just to use a variable. Break false. We can call it whatever we want, and we just use the variable here. So this must be met and break must be false. Then the loop will continue. Here the same. And now if we want to break, we just set break true. Oops. And in principle, for the most outer loop we could break, it has a few differences. So the break breaks in the moment of the break. So here if we would have, for example, something like this, once break is triggered, whatever comes after the break in the loop will not be executed. Here, if we just have the variable, obviously this is not a given. So you would need to kind of break here, and then you would need to check if the break was engaged, and then you would need to break here as well, which kind of makes actually using the break here somewhat redundant. So it would be up to your code design. You would use either the one or the other approach. Doing it like here is kind of, as said, it's redundant. You only need one break mechanism. So maybe it will be more pedagogically valuable to just break this into two samples. One sample and the second sample. So the sample one uses the break variable, and then even though the break was set, the code here would be still executed only after we arrive at the end of the outer loop. We are done. While here, as soon as we break, and in this case we break out of the whole thing directly. And of course you can have an infinite amount of nested loops. So you can have a loop in a loop in a loop in a loop in a loop and so on. I mean, when I say infinite, it's like theoretically. Realistically, you will have at some point run out of memory, and then you won't be able to really have an infinite amount of loops. But the practical limit is so high that it's really not something that anyone can ever reach, at least when writing code by hand. What might also happen is that the compilers, they have some limitations on the complexity of the code. For example, if you write classes with member variables, I think some time ago the limit was like at 1,000 members or something like that. I don't remember exactly, but I know I reached it once, and basically then the compiler just says this would be valid C++, but I cannot handle it. And what you basically then do is you break up your code into, for example, 2 objects or something like that. So there are ways around it. It is not like a killer, but probably if you would make like an computer generated file which would just contain a loop in a loop in a loop in a loop, at some point the compiler would say it cannot handle that file because too many nested contexts or something. But it's, as said, it's a limitation of a compiler. You might find another compiler which has less limitations. And it would be probably also kind of unpractical to have too many loops in your code. Now, the other way, which I mentioned, how you can break out of of multiple loops, is you can use the goto keyword. So we haven't used it, but it's a very, very simple, very basic thing. Basically, what it allows you is you can define in your code somewhere a label. Or let's just really go with the loop example. So we have an infinite loop. Then we have another infinite loop, which we have a third infinite loop, and then we just write go to breakout, and then we need to put this label somewhere. So let's say we want it here, and then it will just jump until here. We could put such a label anywhere in the code, so we could have it here, for example, which kind of would be boring, because then we would then redo the thing and then repeat this thing and then jump here and so on. I mean, we can do it for testing, just for fun. So we see how it works. We don't need this breakpoint. Let's advance to the next one. Okay. So And maybe for speed reasons, we will just step through this code, not through the assembly, because then we can step faster. So we have, of course, our first loop. Then we arrive in the region of our label. Then we do the second loop, and I click too fast. So again, we are here. And then we basically just arrive here inside our endless loop at the breakout, which evaluates to a unconditional jump to the breakout label. And then kind of we still created an endless loop. But the idea would really be that you would have your jump out label after the code. So then if we arrive here, alright, and the thing doesn't like empty statements, which is kind of annoying. So we need to just have a empty semicolon. And as we see in the assembly, once we have this jump here, we just jump out. And the other jump would be to the beginning of the loop, which, as said in this case, we are not, it's a path never taken. We could also add some code here. I mean, then it's not an endless loop anymore, but it will look nicer in the disassembly that there is no, like nothing. It will kind of make more sense. JK. Okay, and suck. And I said this jumps here would bring us back to the increment positions here. And this breakout method, it works quite nicely. If you are writing code in C++, you will run into issues with when using gotos generally with regard to variable initialization and destruction. What this is and how it works, we will take a look at once we arrive at the C++ portion of this lecture. For now, just know that generally using gotos is frowned upon, so it's considered bad practice because it makes your code less easy to understand which structure it really has. So it's kind of spaghetti code things just jumping somewhere. I mean, we could put this, I guess, in here as well. Okay, we can. Wait, I forgot to remove this. I mean, it even did not complain, and basically what will it do now? It will bring us into this loop, which since it was set to 0, will start looping around. Or was it 0? It was something, and then it broke out. But as you see, the things that happen when you're using gotos are very much no longer. Okay, we are here. This was set to 3. Okay, so it will break out after the next operation, and it checks. But as said, the flow is not longer easy to understand. You need to know from where the goto comes, and you can go anywhere. So really the recommendation for any modern language is just not to use gotos at all. And with all the other control flow structures, if switches, loops that C++ and C offers you, there really is no need to do that. So when writing code in C++, I would definitely absolutely avoid gotos. When just writing just C code, they are useful. If you know what you are doing, you can use it. Okay, and the last thing about loops, which is nice to know, is that there is another keyword which allows you to jump directly to the next loop iteration and skip whatever might have come in the loop after this keyword was used. It's called the continue keyword. So here we could can test if this is 9, then continue. So like when break just breaks us out of the loop, continue brings us back to the header directly to the increment portion, and then repeats from there on. In a while loop, of course, it just goes back to the condition and test and repeats that and so on. So let's take a look on our continue here. We put the breakpoint. It never was 9. Interesting. Alright, because we had here a plus plus. So what whatever it will be. First it will be 1, then it will be 3, then it will be 4, then it will be 12. So this must be 12. Zack. And now we have our continue, and the continue is just a jump, like a break, just that the jump points to a different address inside of our memory. So in this case, as you see, it jumps back to the code portion which does the incrementation, and then we have the comparison again. So this is quite useful. And what's also quite funny is that if you have a switch inside the loop, so the break then only applies to the switch, but the continue, since continue is not defined in the context of a switch, the continue will actually make the loop continue, and you can use it from within the switch. So this is something to keep in mind. This might come in handy in certain scenarios. And basically, as you have seen, everything that these loops are doing, one could kind of do by hand with ifs and gotos and nothing more. Of course, it would be much more ugly code, so it's not recommended to do it unless you really need for some strange reason. But what would be a good reason to do it would be a homework. So the homework for this lecture will be from the 20th 03 2025. Maybe I should not say nothing more, because you will need still variables into gotos and ifs. Yeah, that should be clear enough. And let's think about what we will make. Maybe here we'll do it differently. J is 10, J is greater equals 0, J minus minus. Oh, and one more thing. Here in the condition, in principle, we can also use this operators which we learned from the last lecture, like plus plus or minus minus. So for example, this loop could to some extent, let's say, not identity, but some extent, be written as I plus plus I. The difference here is, of course, that the first time you enter this loop, this I was done. So sorry, this code block was done, so the I is already 1. So you get a different value for I in this case. Could also make it like is equals. You could make it like this, which then compares the old value before it incremented. So you can do things, and in principle you can even write I think I is equals I times 2 or something. So you can use the equals operator to assign something and even have a much more complex expression. So, which you, by the way, also can do in a if. So you can have an if which is changing the value of a variable it is handling. Now that said, it's possible. Sometimes it's useful. In most cases, for reasons of making the code readable, it's highly not recommended. Basically, the only use case where it is fine to use assignment inside an if is if you want to save on a variable definition. So if you would have code like, let's do it here, int e is equals 1, 2, 3, if e equals 1, 2, 3, then e is equals 1 or something like that. And you are lazy. That's not good. Let's go with this example. So you have your test variable b okay is equals true if the case is met. And if you want to save on some code, you could write it like this, but that doesn't really save you a line. The problem is what you cannot do is you cannot do it like this, because that doesn't work. What you can do, the only thing you can do, is you can have something like this, but then this is equivalent to checking int e and assigning, of course. E is like 0. So this is pretty much the only case where this is kind of useful. And you need this, for example, if you have a function which returns a value, and then you want to check if the value is not null, and if it is not null, do something with this value. So in this case, such an approach would save you a line of code. You would have here the function call instead of a static value, and then here you would do something with I, because I will exist then within the scope of this if, the same way like the loop variable here exists within the scope of this for loop. But since I said this is usually not recommended and makes code ugly, then let's just forget about it unless we really need to. And anything else to say? Right. What you can do is you can define more than one variable by writing comma. Let's say j. I comma j is equals null. And you even can initialize like both of them, but this syntax limits you to only using one type. So you can use an int. What you could use is you could use a pointer on an int, but you could not use any other type that you would initialize here. So as soon as you end up having something more complex, then you just have to initialize your variables before the loop, and that's it. And this is not that bad, so it doesn't waste too many code lines, and it somehow makes code more readable. So this limitation is kind of fine. But let's return to our example. So we have here our two conditions. In one we will be let's say adding 2 to this. In the other we will be multiplying this by 2. The other one maybe. And capital V. And then here we will have if v modulo 10 is equals 0, then break if it's 2 and null then continue. Then we want to do something else here, so let's say we make here plus plus and here and for the other one we could also have some sort of break condition if e is equals 100, which it probably won't be, but we can have it written here as code. Then break. Yeah, complicated enough. And the assignment is just to basically unfold the thing to do exactly the same things, just one after the other, another, and using gotos like ifs and gotos to jump around. So you would have at some point here like a label at the end, and so to which you can jump, and so on. Is that clear enough as an assignment? Do you have any questions about that? Okay, if there are no questions, then let's save this. Let's quickly see if it still compiles. Yeah, we didn't break anything. And let's start the next project, which will be about pointers. So, as I already shortly mentioned, there are things like pointers, which are basically just addresses. So, but for that we will create a new project. Pointers. Zack. close the other one. Okay, snack. And then of course we so standard includes. Let's also change a few things in the presets, like the last time. General just my code debugging. No, code generation. That is fine enough, but we turn off the security checks. And that's one more setting we should change, which we didn't change before, which makes for nicer code, although it's not yet relevant, so we can ignore it. It will be relevant once we do functions. Here we only need security checks and just my code, I think, disabled for the thing to be clean enough. So to generate clean enough code. So we start again with a variable, my var 123, and as we have already learned, this variable, while it can and often will be reflected in a register, at least in a debug code, it will always have its place in the random access memory of the computer it is being executed on. And this place, this address, is just a number. In case of a modern system, a 64-bit number. On very old systems, it might be a 32-bit number. On small microcontrollers like an Arduino, it might be as small as a 16-bit number. Anything smaller than that will probably never be seen in the wild anymore. So some extra old microcontrollers, they might have an address space of only 8-bit. But since this gives you only 256 bytes that you can address, this is almost useless. And even an Arduino has at least a kilobyte of memory and a few kilobyte of flash, so it needs at least 16-bit addresses, which gives you an address space of 64 kilobyte, which is not much, but it's already enough to do many things. And if you ever have seen Arduino projects, then you see that actually it's quite many things that can be done with this amount of address space and memory. And in fact, most of the very cheap Arduinos, they really will have just a few kilobytes, so they will not even come close to fully use up this address space. And of course, there are bigger Arduinos which have more address space, but these are details. So for our purposes, it's just important to know that pretty much anything reasonably recent will have a 64-bit address space, so every address will be 8-byte long. We can in fact switch here to a 32-bit addressing, so x86 will create a old style 32-bit application with a 32-bit address space. But really nowadays memory is cheap enough that there is really no reason to save on it. So obviously if the addresses become larger and you are using many addresses in your program, then it stands to argue that your program will necessarily consume more memory than a 32-bit application. But the advantages performance-wise of modern 64-bit code are really outweigh the additional memory cost that a 64-bit program comes with. So how do we define a pointer? Quite simply, we first write whatever variable type we want the pointer to point to, and then we write an asterisk, and then we continue like with a normal variable, like myPTR, and we can initialize it with nullPTR. On older C, you would use null, which is just a preprocessor definition, a placeholder that is really replaced with 0. But in modern C, it is a bit frowned upon, so it's the proper approach is to write nullPTR, which effectively this still just gives you 0, but it kind of allows the compiler and tools which might help you to find issues with your code to differentiate between a 0 in the mathematical sense and a 0 as a memory pointer. So if you use here this null pointer, that makes the code less ambiguous, which usually is a good thing. And of course the size of this variable, so the size of a normal int, as we said, it's 32-bit, but the pointer, no matter what it points to, will always be the size of the bitness of the platform. So in this case, as said, 64-bit. And C++ and C comes with quite a nice helper keyword called sizeOf, which you can use. So int my var size, it was lowercase, let's be consistent, is equals sizeOf brackets, and then we can provide either a type or a variable name. And what it will do is it will here give us, so this variable will be filled with whatever size the other variable is. And if we hover over it, the Visual Studio already tells us what it will be 4. And then we just repeat the same thing, just for my pointer. And then we'll see that this will be 8. And now if we switch to the 32-bit, we will see that both are 4. So, as said, you can kind of save a bit memory, but then other things get less efficient. Also, int is like the default type people always write when they want a number, but this really is potentially a source of errors. And if you are handling anything that's an index or a size, then you should always use the size_t type, which this is just a placeholder, and it brings you to either unsigned int 64, or if you would be in the 32-bit case, to a normal unsigned int. So the size t is always the same bitness as a pointer, and even though it might in many cases appear wasteful, it is recommended to use it, because then you really can be sure that whatever value you try to assign there, you will not run out of value space. You will not run into a overflow and then get some negative numbers or something. Plus it's unsigned, so technically it cannot be negative anyways. Okay, and let's now see how we can get a address of something into a pointer. This is quite simple, and in fact this already has been shown in the example in the homework for the casting. So when we open the other thing, variables, here we have defined a pointer on int, we have typecasted the type, and then we have dereferenced it. And here we also had a pointer on float, and we got the address of float using the AND operator. So now we are learning how this code that we used here actually did what it did. So we're using the add operator, and this will, as said, give us the address of a variable, of any variable, instead of its value. So we can here maybe even define yet another test variable. Let's say my some temporary variable. Where is it? Nice place to have. Let's put it here. So the first case, this assigns this assigns the value. And in C++, but not C, there is a third type of how you can use variables. It's called a reference int, and instead of the asterisk, you're using the end symbol, my ref, and then you assign some variable. But what this is under the hood, it is just a pointer. So if the first thing, you cannot have a reference which is unassigned. So you see there is a small red line here, because this kind of is a pointer. I mean, a pointer can be unassigned, but the idea with the reference is that you access the reference just like a normal variable, and the changes will be reflected in what it points to. So with a pointer, if you want to assign a value to a pointer, if you want to assign a value to the variable a pointer points to, then you need the asterisk operator, and then you can assign, let's say 1, 2, 3, 4, 5, 6. If you would write pointers like 1, 2, 3, the thing will first of all complain because 1, 2, 3 is not a valid address. There is just one exception for the number 0, and you will basically assign. I mean, you can force this, but then if you try to dereference the pointer and do something with it, your application would crash. So you don't want to force assign some random values to your pointer. And if you want to assign the thing a value to the thing the pointer points to, so let's start with 0 and maybe go quickly through the code. So we start, once we start and loaded everything here, we can in the locals also see what we see. We see a lot of uninitialized stuff. We have here our 0, so this is 0. Then we have our pointer, which is then initialized to 0. Then we have here these two helper variables we don't care about. Also, you might notice here that in the assembly, this size of it's not a function or nothing, it just is replaced with a static assignment of a value. The compiler just knows the size and then just makes it's equals 4, it's equals 8 or whatever. Right, so here we have our, here we are assigning the address of our variable to my pointer. So now our pointer, as you see here, has a larger number, which is the address in memory for this application. So one thing to know about addresses on modern systems is that every application has its own address space. So if you have another application, it might get some memory with the same address, but those memory blocks physically in your computer will not be in the same place at all. And the operating system is managing this. So normally the way this is arranged is that from the entire address space that you have from 0 to 16 Fs after each other, that's some 16 exabytes something. Usually this address space is split in half, and the lower portion is used for applications, and there every application gets its completely own address space. So the applications from each other are fully separated. There is no way how they could influence each other except if it is specially assigned, not assigned, it is specially set up this way by the operating system. So you might use special function calls which will allow you to generate memory, which then will be shared amongst multiple applications. But this is something that needs to be set up intentionally, and you need to be able to access the other applications and so on. So it's not something that you can try to exploit. You really need the operating system's permission to in any way interact with any other application on the system. Now, the upper portion of the address space is reserved for the operating system kernel. So the idea is that the operating system will use this upper portion of the address space to place things which which are needed to have the same address for all applications. And on 32-bit systems, this limitation meant that a application, even though the address space is nominally 4 gigabyte, that a normal user mode application could allocate at most 2 gigabytes of memory and nothing more, even though the second half might be mostly empty. On modern 64-bit systems, these limits are so insanely huge that you will not arrive at half of the address space ever anyways. So this is something just to keep in mind when working with addresses, that usually those addresses will not be the same, and even if they are the same, it doesn't mean that if you write there, you could write to another application. You cannot do that. This is prevented on a hardware level through a mechanism called memory protection. There is a special hardware unit in the CPU called the memory management unit, which manages this, and we will take a look on memory management in a later lecture. But for now, it is just important to keep in mind that every application gets its own addressing space completely for itself. Okay, so we got an address here as set for from our variable, which is now stored in our pointer. Then we have, of course, the other operation which will just copy the value. So we can see here how this works. So here, if you want the address, we are using the layer instruction. I think some of you asked in the past already what this layer thingy is doing. And it is used to load an address. And in this case, we just load into the rex register the address of this variable. When we hide the symbol names, this becomes a bit more understandable. So we have the base pointer for our current stack frame. What this is we will learn once we are looking into function calls. Just enough to say that when we enter this function, one of the registers contains a memory address, which will be like the base address for the current block of memory in which we are operating. and our variable here, that was this one, was allocated at the position base pointer value +4. So the layer basically just as a mathematical operation. It takes the value of the RBP register, it adds 4 to it, and then it saves this into the rex register. And then of course the value is saved to the memory wherever our my pointer lives. While the other thing here, the assignment, it uses a move operation to get into the ARGS register a value from RBP, but it dereferences the value. So it means it will first do the same operation that layer does. It will compute the address, the final address, but then as a next step within the same step of the operation. So the CPU usually breaks up complex operations into multiple sub-steps. So it will do the same thing that layer does, but then it will have an additional sub-step in which it will ask the memory controller to retrieve the value from whatever address it has calculated and then store this value in the EAX register. And then of course here likewise we save to the next variable, which lies at the position at the next position in our memory block. Now if we proceed with our sample here, we arrive at the dereferentiation line. So here we use the asterisk operator to write something to the location pointer points to. So when we step over those instructions, you will see here that pointer itself will not change, but var will change to 1, 2, 3. So we step once, we step twice, and we see here that var changed, and it here shows it in red, but it shows it only in red because when it's a pointer it also shows you the pointed to value, so only the thing in the brackets changed. So it's kind of nice that you don't need to watch all the variables. What you can, by the way, do is you can switch to this watch 1. You can also add more watches and then define your own variables you are interested in. So obviously with the simple applications we are writing here the locals, which just shows you all the local variables, is of course good enough. But if you would have like 100 variables, that might be a bit confusing. So you could create your custom watch views where you would only enter a few variables about which you want to get the information right now, and you can ignore the other ones. Right, so that's that. And now the next thing, this reference. And you see here that this reference, this initialization of this reference looks very much, actually it looks identically to how the assignment from of the address of a variable looked like. Of course here the second line is slightly different because the RBP is different because it's a different variable, but effectively this thing and that thing kind of are the very same thing. But as you see here, to this reference you can assign directly. Don't use the asterisk operator, but if you do this, we step over, we see again that value here var changed, because effectively this reference mechanism is like a way to abstract away the pointers, so that if you don't want to use pointers explicitly, but it's in some cases you will still need to be able to change values of some other things, you can use such a reference. The main difference is that here when you work with the pointer, you can change what the pointer points to at any point in time. So we can, for example, define another variable. Let's call it myvar2. Or let's use this variable, mytemp. It's a nice variable. So we can just at any point in time switch my pointer to my mytemp, and then asterisk my pointer is equals 789. I forgot the semicolon there. And while here, so this to my var, while this, oops, this assigns to my temp. So you can use one pointer and then make it for some portion of your code execution assigning things to one thing, then you can change the pointer and then make it assign things to other things, which is extremely powerful. And of course, opportunity to make mistakes. So always when using pointers, one should be very careful not to do something, what's unvorsichtig on English? Uncareful? One should be careful to not do something careless with the pointers, because a huge amount of security bugs and also just normal bugs in applications which cause unpredicted behavior or crashes is often caused by the improper use of pointers. So it is one of the most powerful aspects of C++ and of C and C++ that you can use memory really directly, but the fact that you have to manage the memory yourself is risky if you are not careful what you are doing. Of course, when you are using memory safe languages like C#, Rust or something like that, you are trading in flexibility for security, which in some cases is okay, in other cases it's not okay, because it's a huge pain in the butt to write code in Rust in comparison to C, at least in my experience. I'm sure there are some Rust proponents that will oppose this opinion, but I would generally say that if you're writing some code for your own use or for a smaller audience, it's much better to use something that allows you to write efficient code quickly, even if it's not perfectly safe. But if you're writing like something for millions and hundreds of millions of users, then you're probably not doing it alone, and then you're doing it as a part of a large corporation, a large organization, in which case you can afford to employ 30% more people or whatever you need to make them work less efficiently but produce more safe code. And this is a trade-off which for things like an operating system or a web browser is very well justified. For simple single-user scientific applications or for small utilities, even if they are used by a few hundred or even thousand people, it's, I think, really better to do something that you can use your time in the most efficient way. Writing safe code with cumbersome languages is not efficient, it's just safe, and it's just a trade-off up to what your goals are. But enough rambling about that. Let's continue. So first of all, are there any questions to this pointers and references? Yeah, C# has pointers. That's true, but usually you are using. So they are, first of all, they are reference counted in C#. So they will not. You will not end up pointing to things which no longer exist, or just having invalid values inside your pointers. That's one thing, and I haven't used Rust much, so I won't say anything about that. Yeah, okay. So the next comment in the chat, you can use in different languages like structures that allows you to use unsafe pointers or unsafe code. So that is correct. In C# you can define something that will give you the ability to use a pointer, but that's like it's a workaround. It's not how you are intended to write most of your code. You can use this, and you're using it often when calling some C API of Windows, for example, but you would rather not use such raw pointers, unsafe pointers in your normal program logic, while in C++, while in C you only have normal pointers. In C++, you can use smart pointers, which you can either create yourself, or you can use already pre-created smart pointers like from the STL library. So you can be safe in C++, but this is then a choice and not a and not kind of enforced or at least recommended by the language. While in the memory safe languages like C# or Rust, you can for the purposes of interfacing with C code and other unsafe APIs use pointers, but this is not something that you would do in your normal program logic. Any more questions? Okay. Since we don't have more questions, let's then continue to the next thing. So we had our variables, we had our pointers. The next useful thing, of course, would be arrays. So if you, let's say, need a few ints, like if you want to save somehow 10 numbers and then go through them in a loop, you would need some sort of array. So in C and C++, you can create very simple arrays just by writing the type you want in the array, then a name, let's call it my R, and then use the square brackets, and then you specify the size. So let's say 10 elements, and this would be the simplest way to define an array. What you can do is, of course, you can also assign initial values. So the same way as you can assign one initial value here to one single variable, we can, using the curly brackets, assign multiple values to all the entries of an array. And the way this works in the code is that this array in the most cases will behave like a pointer. So before we do that, first we will just let's just create a loop. Int e is equals 0, e is less than, and now let's take the element count. So unfortunately there is no keyword that does this for you. There are some preprocessor definitions that do the same thing, but if you want to know how many elements there are in an array, you can use size of the array and then divide this by size of one of the array elements. So either you could just write int if you know the type, or you can write array 0. That will then take the type of the first element in the array. They are all the same, so this is good enough. And of course we have our I++. And then let's say, okay, we have our my variable from the beginning. Let's reset it to 0. And then here, let's assign it. We will sum together all the values. So we take the array, we use a square bracket, and then we specify the index. And this will give us the value from the array at this position. So maybe we should have initialized this with something less boring. Oh, and I see we forgot one value. Okay. And as simple as that. So the square bracket operator gives you a value from the array. The main limitation here is that this array has to have a fixed size. So you cannot create an array of a random size locally on the stack. You would need to allocate it from the heap, which and memory allocation is a subject for let's see, is it the next lecture or the over next lecture? Structure functions for the over next topic. So the next, actually two topics in future, but I think we will manage to make pointers and structures during this lecture. So next lecture will be functions, and after functions we will do memory management, when we will then really see in detail how you can create arrays of arbitrary size. But as long as we are defining them within the function on the stack, they have to have a size which is known. You could use a const variable or a preprocessor definition as a placeholder for the number. So there are ways to make it nicer. For example, if you would have something where you would have like a larger code and you want to initialize multiple arrays all to the same size, and you want to avoid the bug that if you later change the size, you forget to change one of the places, and you could use a preprocessor definition or def my array size 10, and then use just this instead of the number. And then if you have other places, you can use it. And also, by the way, you could also then use this definition here as well. So whatever you prefer. Also, there is the if you include Windows H, there will be array size, which is, once we get there, defined, it just doesn't want to bring us there, which is basic. That's a new definition of elements. At some point it should be, it will, yeah. at some point it brings us to the same trick we did before by hand, but it actually takes us over multiple levels of definitions. So you can, if you have Windows 8 included, you can use this array size, and many other frameworks might have the same or similar placeholders, since it's quite useful to be able to get the size of an array. Now, as I mentioned already before, the array kind of behaves like a pointer. So if we just take our, or maybe I should say maybe a pointer behaves like an array. It's kind of a historical question, which is which. So we can use our pointer, and then we can just assign our array to it, and it will be just fine. And then we can use the same loop here to access the values of this array using our pointer. There is, however, one important thing to keep in mind. If you try doing this, that will not work. This will not work. This will fail, because size of pointer, as we have said, is 8, while size of array is, as you see here, it's 40. So this is something which one really should be very careful with, that this size of and this tricks to get the size of an array really only work on the array variable itself, and not on anything you might have assigned the address of the array to. So on the CPU side of things, the program doesn't know how much memory this was allocated. So if we basically, for the program, we have just a blob of memory where we have this variable, those two variables, the next variable, the array. We could define this as yet another variable. So int asterisk my oops, it's not typing. Int asterisk my so if we would break this, if we would go too far. So one thing, for example, also one thing I forgot to tell you, which I think is, I mean, for me it's obvious, but for people that might be beginners, it's not. Arrays are indexed from 0. So the first entry in an array has the index of 0, meaning that if we have here an array with 10 elements, then the last element will be addressed with the number 9. And this is why here, for example, we are checking whether I is less than 10. So as long as I is less than 10, it is fine to access it. And if I would be 10, so let's make this equals, this will write to a memory location which is after the array. So we can put a breakpoint here. Now, of course, there are a few practical considerations which might break this demo. But if we now have, so here, first of all, the upper loop worked fine. It ran 10 times. It added values here to our myvar, so this is fine. But now if we run this 11 times, the last access, since we have here n is equals, will be to kind of an element after the array which does not exist, and in all likelihood the element will be this variable here. So and we forgot here to change this, so let's quickly change that. So I said you can use the pointers. My background. Okay, so let's run this. Let's just the plus. So for now, we are just progressing, and our reference and our variable are changing from the array. Sorry, we are not. We are just reading from the array, so we will not destroy anything. But let's continue until we arrive at the 10. So this is a not valid index. And here, when we now try to read something from this, so let's see. The last value of this thing was well, 90, which is a reasonably small number. And if we now step over it, the thing, as you see here, became -8 something something something. And the reason is because we read from a memory which does not longer belong to the array. But as you see, the program didn't crash, nothing happened except the unpredictable behavior. So this is something where one has to be very careful when using pointers, especially pointers to arrays. is that the pointer only contains the address. It does not contain the length of the array or any additional information. Meaning that if you are just accessing the pointer by the next and the next and the next and so on value, you can easily access memory which lies somewhere far beyond what the array points. I mean, we could even enter here like 100. It might not even crash. So at some point you will arrive at a memory address. So again here, as you see, we executed the I 100 times. We read a lot of memory, and still the CPU did not notice that something bad just happened. Generally, of course, when you are writing modern C++ code, you should use container types for arrays. Yes?
If we do the same in the loop above, where we access the array elements directly, we will get an error, or what will happen?
It will still ignore it. We can just do it. It just ignores it. It does not check it. So here, in principle, the compiler could know that this thing well has a size of 40, but at this point the compiler doesn't care, because it would need to kind of reproduce the whole, how to say it, the compiler would need to step through the whole code and generate all the possible values what I might be. In this case it's simple, but as soon as the index would be a result of a more complex operation which includes additional parameters, then it is not longer trivial, and generally you will not have the worst bugs in such a situation where you are using just a loop from 0 to 10 or from 0 to any other number, but somewhere where you're actually generating and calculating indices. So there is no point in trying to find this. Here in this case you see that it actually is underscoring it in green, and it tells you that index 99 is out of the valid range. So the Visual Studio itself, the IDE, the editor, it kind of tries to catch such simple errors and tell you about them. But the compiler, which then really generates actual machine code, it just doesn't care. And this is kind of, as said, reasonable, because it would not be able to catch the more complex cases anyways. So if we here, we already fixed that. We can run it again, then it should stop complaining. Although this IntelliSense, it's still complaining. Now it reset it. So sometimes it resets this green warnings only once once you recompile the code. We can put a breakpoint here and compare how the code looks like, and we will, for example, see that the code here and the code here, they look almost the same. So they should actually do exactly the same. So let's see, except for address. So it takes, of course, from a slightly different offset a value into rex, then here it takes the second value. So which one is which? Let's show the names. Doesn't, okay, so my ptr 100 and 100, these are different. One myvar, okay. So the last one is just a myvar. So for the initial part will be getting the value from the array. So in the first case, we get the value at this address into rex, and then here we access it plus 100. Where's our incrementation? Move sx e. That generates a few asterisk 4, and then it has the value here. Then it loads it, then it adds it, and it saves it.
Excuse me. I have a
Yes.
question regarding this syntax when you access like a certain value of the pointer that points
Hmm.
towards the array. Because like I think the pointer itself should point towards the first element of the array only, right? So does it automatically dereference the value when you use my pointer square bracket I, or how is this working?
So we have here this thing here is equivalent to writing 0 is equals. So whether you write asterisk pointer or you write my pointer square bracket 0, it will give you the exact same thing. It will evaluate to the exact same code. We can quickly demo that and then return to the other one. So semicolon, breakpoint. Okay, it should be the same code. So this one just the references. Okay, it adds a multiplication with it makes it more complicated, but effectively it is the same thing. So you have you load the value from my pointer to rex, and then it does the assignment, and then here it makes ex4, then it ex here move, then it multiplies rex and rex and zeros, which ends up being 0. This is a bit wasteful when we try to do it as a release build, although then it might optimize too much away. Let's see. Stack semantically is the same thing. How the code I said ends up. Okay, this optimizes too much away. Let's say that bug build. Semantically, these two lines are identical. The generated code, as you see here, is slightly different because it kind of tries to make what it tries to do. Let's write it in the different way. So my pointer plus 0 asterisk is equals the same name. So these are basically 3 ways how you can write the things to have the same effect, and those 2 you could also use if you want to if you have an index. So for example here you could write it like this. This would give you the same thing, and then let's again see what the compiler does. So in the first case, so here in the first 2 cases actually it generates the same code. In the next case, even though it could generate the same code, it decides for some reason to not do the same thing. So first it loads the value 4, which is the size of a single step into the AX register, because as said here our int is 4 byte long. Then it the first one will be the result register. Then it takes the rex, and AX is kind of the same thing. It just depends on how many zeros you have on the beginning. So this is equivalent, and then multiplies this with 0, which gives you basically the value 0 in the rex register. And then it ignores the rex okay, and then here it uses a syntax where it can use like 2 registers. So you can either have like here a register plus a number, or you can have a register plus a register. But rex is basically 0, right? So what it effectively does is like here. So in rex, in the end, so no, let's say different. In rex here you have directly the address, while here you have the address in RCX, but you make RCX plus 0, and this ends up being the same address, and then it makes the move operation to assign the value 789 just in hexadecimal notation. Why it does it this way, I'm not sure. It's, I said, very wasteful, and if you look into documentation and manuals for C++, they will also generally tell you that asterisk PTR and PTR from 0 should be exactly the same thing. In this case, the compiler decides to do it in some convoluted way. As said, probably when building for a debug target, it would optimize that away and it would look the same. But then, since this code here is like we are overwriting the same value, then the compiler is smart enough to know that only the last operation is relevant, so it would remove all the other lines completely from the resulting code. So we could play around maybe with some optimizer settings so that we could maybe generate code which is just slightly optimized. But I think this, given that the modern compilers are very much made to be kind of a black box that just gives you optimized code, I think that would be a waste of time to try to look into that in detail. When we run it again, what we also can of course compare is this code further down. Where were we here in our loops, with which we started, by the way. So here it kind of the symbols. Loop 1, loop 2, yeah. So here it again they did it slightly differently, since it then uses to registers any multiplication inside the instruction. So they have in the x86 assembly language, there are really many ways to get to the same result. So I think this might sometimes get a bit confusing, but you just need to step by step through the assembly and write down what it's doing, and then it's quite understandable. But as we see here, it in some way sometimes does not generate the same thing. I mean, if we would use a different value here, like let's say 1, I mean we don't have a 1 here available, but because we only had a pointer. But here then the generated code kind of makes sense, because it will then have 4 times 1, or if we would use 2, then it would be 4 times 2, and then here adding this would be reasonable. But then again, in the same vein, if we look to the other place in the code where we have a similar code like here, here it decided to do it differently. So why the compiler sometimes chooses one way and sometimes another, it's something only the people that wrote the compiler know. Functionally, this all is equivalent, and because in the end it will generate the address which is pointed to, and then it will write a value to it. Okay, but where were we? Yes, we wanted to compare those two before we change this. We wanted to compare those two with each other. So here we have the array directly, and here we have a pointer to which we assigned the first element from the array, the address of the first element from the array. So in principle, this line could also be written as reference null. This would give you the same address, and actually now I'm interested to see if the compiler will actually generate the same code, or if it will decide to make different code again. And interestingly enough, it's still here chose to use completely different ways to effectively arrive at the same value. So if we print the value here out, we see that it's the exact same address that those two different code implementations yielded. This is often when you use old code, you sometimes see exactly such a thing used instead of just assigning the array. And interestingly enough, at least in the debug build, that actually yields a less efficient code implementation. What we also could of course take a look at is how this would look if we switch the compiler to a 32-bit compiler. If it would then decide to use other optimizations in the debug build. It needs to load some symbols, since the libraries which the program now will be using are different between the 64 and the 32-bit mode. Okay, so we see here that it still opted to use the same not identical implementation, even though it ends up with the same values. Just that now, of course, the values are much shorter, so the address is only made of 32-bit. Okay. Right here. So this was one thing. This we can comment out. Right, and we wanted to step through this loops to see how they are doing. 64-bit again. Zack. Okay. So let's try to analyze the code. So first of all, it takes a value which from the stack, so where the RBP plus offset points to, saves it into the rex register. It doesn't tell us which variable that will be, but we will see this shortly. Then it makes a calculation, so it takes the value in RAG. So let's make a step, see how much RAG. So that probably will be I. Yeah, that is I, which it takes. Then it does here the calculation, so it takes the base pointer plus I times 4, which will give us the right addresses, the right next address. So in this case, of course, since RAX is 0, this will give us the same value as we have anyways. Step. So now in ARX, that still will be, I think, just the of. Wait, let's see. ARX contains 1. Yeah, because we had 1 here, so it took the value from the array. Then the next step will be it will get the value probably from our my value. You can see if there it has the name. Yeah. So sometimes it shows you what it does, sometimes it doesn't. So here it tells us that it is taking the my var value into EAX, and then it adds them together. For whatever reason, moves from ECX to EAX, even though this operation here could be just as well here with ECX directly. But it uses one unnecessary operation. And then, well, the value is then saved basically back to the same address. And now when we go to the next code block, where we are using the pointer. Oh wait, that was not right, that should have been I. Yes, right. So we go to the next block. Need to remove the breakpoint there. And then we compare the operations. So again, we get here the I variable, I guess, then ECX, AX. So let's first step. Zack. Axis 0. Then it will load something into RCX. It loaded probably the address, so let's enable hex display. See it again. So 32278 something something, and the address is yeah. So here it added in an extra step, loading from this variable its value that it points to, and then the next step, similarly to here, it does a addition of 2 registers plus, although here it even had an additional offset. So if we want, what we can do is we can take those bytes and put them into our online disassembler to see what this exactly does. So as you see here, it really has 4 operands. So this is quite a complicated operation, while here those few bytes are considerably simpler, since they only have 3 operands. So while in the uppercase it used since this offset, which points then always to the base address of the array. In the lower implementation, it implemented it differently because, as I said, it first explicitly grabs the value that the pointer points to, and then does just a offset addition and multiplication. And then once this is done, of course, the rest of the code looks the same. This is somewhat an optimization, although how much of an optimization this really is, one would need to test this, because as said, each such complicated step internally will be broken up into individual smaller steps inside the CPU. So one long opcode might need more time to execute than two shorter opcodes, although this opcode here, at least with regard to the amount of bytes, is just as long as this one. It's just missing some additional operations, which then the next opcode executes. So probably the upper version is indeed slightly a small amount, slightly more efficient. Okay, good. So we had this, we had that. Generally, with regard to efficiency, nowadays, since the compilers are so complex and are doing a lot of things on their own, the best approach is just to benchmark your code. If you have some code which needs to be fast, then, and you know that there are ways you could change it to maybe make it a bit slightly more efficient, then well, either really analyze the assembly output, but this is a very laborious task, as you see here. Even in such simple examples, it takes a long time to see what it exactly is doing, or really just benchmark it and then go with the fastest, with the thing that gives you the fastest result without thinking about why exactly it is faster. Okay, so we have this, and as we have seen here also, this line could be written like this. It would be would be kind of the same thing. We can actually put a breakpoint here and see if this gives us, and this gives us in this case really exactly the same code byte for byte. So this and this is really equivalent. And the lower case is actually quite useful because it allows you to go through a array in a slightly different way. So for example, let's always reset our variable before we write to it. Oops. It's like, okay, now let's do it slightly different. For have my ptr is equals my array. So we start here again. Semicolon, then we make my ptr, so we take the address we have here, and we say that the address must be less than the starting address plus the count. So the compiler will, so here the compiler will enter the number 10, and if we have this plus, it will not do a operation like plus 10, but it will actually make plus 10 times array item size. So since the compiler knows that my array is of type int, if you make this plus 1 or plus anything, it will always do plus in not like in 1, 2, 3, but in increments of in units of whatever your array points to. So this is quite useful, and it's called generally just pointer arithmetics, since you can do operations with pointers. The same way, if we have a pointer and we make a plus plus or a plus 1, it will advance not by 1 byte but by 1 element of whatever the pointer points to. So here inside our function, since my pointer in the upper case we have had always one pointer, and we're doing the pointer arithmetics kind of implicitly using this square bracket operator. Here we are doing this explicitly using the plus plus. and then we just dereference the thing. Then we have here this plus plus. Also, we could maybe move this here so that we have the code in one place, and then when we run it, we can see how much code this generated. So as you see, it is still quite a comparable amount of code to before. Here it's actually quite a bit more code, because it explicitly loads the thing into a register. Then it, even though it's plus plus, i.e. +1, it makes here add 4, as I said. If this would be a variable of a different type, for example a 64-bit integer, then it would be +8, and then of course it saves it, and then the dereferentiation here again works in a simple way. Okay, so when we can run this, it will also run until it terminates. So if you have pointers and arrays, there are quite a few ways how you can access the members, how you can iterate through the whole thing. Generally, so this code here should be, when it's fully release build optimized, more efficient than the code above. Although that also probably depends on the level of the optimization, because if the compiler is smart enough, it could even decide to rewrite the code if this is such a loop with a fixed end value. If this would be a more complex loop, especially if this would not be a number but some variable that is taken from somewhere else, and of course the compiler could not do such a trick. But the most efficient way would really be if you could just advance the my pointer, and then not have it always saved back to memory with every step, because this really makes it kind of generate more code than what you are using here, since here some of the intermediate values are just kept in registers, which is much more efficient. Okay. Any questions so far? Any more questions? Okay. Okay, no questions, so then let's continue. In principle, since we already finished the pointers, so maybe one more thing. As we have seen here, we can use pointers to cast from one type to any other type, even though the conversion would not be normally permissible. And in a similar way, what we can do is, as you know, we have this const keyword, which allows us to define a const variable, one which is not supposed to be changed. And a thing you can do with such a const variable, since let's make it 10 again. Since it's not supposed to be changed, you can use it in an array. If this wouldn't be const, you couldn't use it, because this needs to be a fixed number. But if it is const, then the compiler knows it will always be 10, and then it can just take the 10 and put it in here. And now what is kind of not so great is that you can take the address of const, because since it's a debug bit, it will have a address somewhere in memory, and then say you cast this on int asterisk, not const int, and then assign to it, let's say the number 20 or something, and this it will assign the number in the memory at some place, but here it will not have an effect. And if we, in fact, let's do it like this, this will still effectively here just take the value number 10. It will not be able to you will not be able to influence that. So let's copy one of our loops. Let's say, let's go with this one, and of course we need a different name, otherwise it will complain. Let's say array2, and here if we say const then let's see what it will do, because probably at this point it will still refer to the memory. Yeah, it does. And effectively, then what we will do again is the situation where you are reading past the end of the thing, and then getting values which shouldn't be there in there. So you can unconst a const, but this doesn't mean that this will work, because as said, in some places the const is just takes the number and not the memory address. So this is something to keep in mind, that this is not safe. And what else would be interesting to do? With pointers, I think there's maybe one more thing that we can also try. So we have our, but I think I mentioned that already, the endianness of numbers in modern computing. So we write the number 0x1, 2, 3, 4, 5, 6, 7, 8 here, and then we define a char asterisk my chars, let's say, and then we use our newly gained power of casting to cast this to an array of characters, and then let's get char 1, the 4 characters out of our 0 to 4 to 4, 1, 2, 3, 1, 2, 3, sorry, 2, 3, 4. Okay, and let's run it. And yes, I forgot the AND operator. So effectively what I did is, let me run it again. The pointer, the value of the pointer is just 1, 2, 3, 4, 5, 6, 7, 8, which is not a valid address, apparently. And the whole thing crashes once it tries to dereference it. And the thing is that it here did not even complain that it's not the right type. It just did it. Rebuild it again. Yeah. Doesn't even... Okay, it throws one warning, but it allows us to compile. This is why, if you want to be somewhat safe, it is recommended to treat warnings as errors. Unless you're really writing like a program just for temporary use in a lab, I would really recommend to enable this. It might be sometimes a bit annoying, but it really allows you to avoid many mistakes. And as you have seen here, it's easy to make such a mistake. Okay, so now it should work. We have our chars, and as you see here, the way this thing is structured in memory is 7, 8. It's like this, which is kind of counterintuitive. And if you want to read up on this, there is a Wikipedia article about that. It's called endianness, and you have little endian and big endian, and it pretty much just defines you the order. And the big endian would be the order that like a human would, I guess, intuitively prefer. So this one is the little endian. And pretty much all the modern CPUs are little endian. There is no major CPU type nowadays that would work by default in a big endian mode. For some ARM implementations, you can switch the CPU during the early initialization state to big endian, but there really usually is no use for that. The reason why this little endian is preferred is quite simple. So if we have this, let's say we will copy this again, but we use a smaller value. Let's say 1, 2, 3, 4 A, B, C, D. Then the thing here would be C, D, A, B, 0, 0, 0, 0. Of course, this one here is 0, 0, 0, 0, A, B, C, D. 1, 0 too much. And if we now take a shot, and assign this value, it is still correct. It's A, B, C, D, because the way all these operations work is they take the memory at the first offset and copy 1 byte or 2 bytes or 4 bytes or 8 bytes and so on. So if you are assigning something to a smaller variable, then you kind of get some sort of fault tolerance built in, such that you don't end up, because if this would be big endian, then this assignment, if it would be done in a simple way, like just with a move to register and then move out, then you would end up with the zeros in your variable, which would be probably less useful. And often, or at least it was common more in the past, not so much nowadays, that you are sometimes having some bigger variable and then you just get the smaller part of it if you know that it won't be too big, and then you make such assignments. Of course, nowadays you would want to always use the right type and not risk a value overflow, but it simply kind of appeared to be more efficient with regard to fault tolerance to make it this way, even though, as said, it is kind of unintuitive. One place where you will find this big endian notation is, for example, when you have communication over network, usually network protocols are specified to use integers in the big endian notation, most notably IPv4 addresses, for example. But realistically, if you are writing some own protocol, you probably will not care for that, and then you will just serialize your integers as you have them in your system, and then encapsulate the little endian notation directly. So yeah, that's that. I think let's leave this in here, and let's, unless there are any questions, let's continue with the next subject. Although next subject, the structures, I wanted to do them today, but this is quite a lot of things, so maybe we'll move the structures to the next lecture, and then the functions will be moved one lecture further. And as I promised earlier, I will show you how to implement simple test cases so that you can test your code. I think this will be more useful. Let's create a new project for that. Alright, variables we don't need. Here, just open the flow control so that this remains open. Here, let's create a new project called simple test. Okay. Don't need it. We don't need that. Okay, so we have what can we do? We have variables. We have gotos. We can use pointers if we need to. Okay, I think we are well equipped for that, even though we don't know functions. So let's see. First, let's think about some assignment. Let's say write a code which what adds to numbers. It can be as trivial as can be, or maybe no, which calculates which is the power of an integer. That's a nice assignment. So and we have arrays. That's even better. That gives us even more that makes us super powerful. So let's say int my input 1 is equals one thing I forgot to tell you about the arrays, which I should tell you. Pointers. Right. You can define the array like this as well. You make square brackets, you don't say how many elements, and then you initialize. Because here, if you now add a 11th element, it complains because you have too many elements, right? It's not 10. But if you don't tell it how many elements they are, then you can add as many as you want, and it will just give you this amount. It will basically just count how many you have, and then enter this value here for the compilation. So this is kind of useful as a trick. And of course, if you're initializing, you can always initialize less than the amount of elements. But then still, if you have a number set, then the array will still have all the space. It will just not have some of the values. Okay, so we have our input 1. Right. Is equals, and let's say we want 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. And then let's say we have our input 2. And this will be to which power we want it. And let's say we want to power 2, 4, 1, 6, 2. We just select some random numbers with an honest throw of dice. And then we make another array. Call it my expectation. Far too long. My x output. Okay, and now we need to actually compute our expected output since we want to create a test case. So 1 to the power of 2 is 1, comma 2 to the power of 4 is 2 to the power of 4 is what, 16, I think. Let's use that calculator. Let's make things faster. Oh, this is a bit too big, so wait, does this do powers? No, it doesn't. We need to switch to the scientific one. 2 to the power of 4 gives us 16, comma 3 to the power of 1 gives us 3. 4 to the power of 6 needs a calculator. 4 to the power of 6. That's a large number. Okay, 4 to the power of 6. 5 to the power of 2. That's 5 to the power of 2. That's 25. Then 6 to the power of 3. 6 to the power of 3, that's something. 7 to the power of 1 is 7. 8 to the power of 4. 8 to the power of 4, that will be very big. Wait, did we have that already? Apparently one of the other ones, which one was it? This one. 4 to the power of 6 apparently is the same. 4 to the power of 6. Yeah. Yeah, 9 to the power of 2, that's like 81, I think. 81. And 0 to the power of 6 is 0. Okay, so we have our expected output. Now, we don't even need to use Go, because we can use a loop, since we know how to do loops. And as I said, we should use size t if we are using indices, even though those an int would be just fine, just to be on the correct side. E is less than let's include Windows. Array size. It's full with array size. Let's take the output array. We could use any of those. It doesn't matter. They all need to be the same size anyways. I++. Okay, and now well, we could use the math.h to just use the function power, but since we are not yet since we not yet officially know how to use functions, let's write our own power functions. So int a is equals my input from E, b is my input 2 from E, and well, let's call it maybe I1 in 1, in 2, and out. Int out is equals 0, and we will do the power calculation like on foot. So for int j, let's go with j equals 0. J is less than so this to the power of that. So input 2 is into times if this is 0. It was of course a special case which we didn't cover. Okay, since which one is boring? Yeah, this one is boring. 7 to the power of 1 is 7, so let's say 7 to the power of 0. 7 to the power of 0 is 1. Right, wait, so we have, if this would be 1 and would do 1, okay, so this is good. So this needs to start out as no, it doesn't. We will make it work. We will ignore this case for now. J++. Okay, so this loop will be executed however many times our exponent is. So 2, 4, 1, 6, 2, 3, 0, and so on times. And each time it's executed, it takes the old value. The old value needs to be initialized with something because it is multiplying with itself. So if it's to the power of 1, that's also a special case. So let's start with 1. This will be initialized. The first input is the thing with this thing, but then we don't cover the 0 case properly, but we'll add later. So we start with this thing, we then start at 1, and then we make output is equals is string equals output. So the thing is multiplied with itself. Or we can also write it down, maybe like sorry, not with itself. It needs to be multiplied with the input value, of course. Yeah, that's correct. And since it's such a short code, let's keep it like this. Okay, we keep this spatially separate, and now we make like if output is equals our expected output at E. Well, that's the okay case, and that's the fail case. And since we don't know how to use functions, but we know how to use arrays, we can use boolean my test, or my result, my test. Let's call it my test 10. And this is not initialized. This is fine not to be initialized. And then we don't need the square brackets. My test from E is equals true, and here it's equals false. Although we could also simplify the code, of course, and just write this like this, but I prefer that since you could then easier replace this with a line to print something or something like that. So I will even keep it like this, and then at the end put a breakpoint, and then we can inspect our test, which should contain all ones, although not quite, since we have at least one bug. So let's see. Yeah, we see here true, 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 false, true, true, true. So we are not properly handling the special case where the exponent is 0. So we need to do this now. So basically we learned that something went wrong. What we could do, if you want to print to screen, even though officially you don't know how to use functions, we can use printf and just write okay. And you can use this printf. We need stdio for that. stdio. So if you want to use functions, then you can. Oh, and of course that's okay, but it's fail. Then it will of course print to the console. Okay, fail. Okay, and then and I would leave it at that. You can put a breakpoint here so that the whole thing breaks when you get the error, so then you can inspect the values and see why it failed. So once we had the functions calls, and then the next lecture about strings, then I will show you and explain to you exactly how to use printf and string formatting and stuff like that. But until then, I think for your test cases, until then it is fine if you use it basically by having a variable which then takes the results, and that's it. We could also pre-initialize this with false. And the nice thing is that put a breakpoint here. That even though we have initialized like with one element, it already initialized all the elements for us. So if we don't initialize it and run it, you see here that actually the value, while it says it's true, it's actually 204, which is a placeholder for uninitialized memory. So here, when we look in here, it's written somewhere as a loop, perhaps here. It is writing the CCC pattern everywhere, and the CCC pattern evaluates to this. In this project, you have not turned off all the additional things. If we would turn off the basic runtime and time checks and a few other things, then it would not pre-fill the memory with anything. And if we initialize this to true, it will nicely enough only initialize the first to true, I'll initialize all the others to false. And the way it does this is that for pretty much all of the types, you have a default value that it takes if it initializes it at all. And if you initialize an array, you don't need to initialize all the members. If you only initialize the first few, it will take the standard default value for all the other values, which basically always is 0, or in the case of ball, it's false. Okay. So right, so we have here a breakpoint, we have this. Alright, and we need now to fix the bug. So we have seen that our code fails in this special case. So how do we fix this? We make first of all we make this, and then we make just, for example, an if in wait, would that work? That would work, huh? We just need to initialize 1 with 1, and then it will, and start this at 0 again. Then it should work for the cases. Did it? Yeah, I didn't fail, and it's true. So we have introduced a bug, and then we have troubleshooted it successfully, and the way it's implemented here constitutes already the simplest way of implementing such a unit test. Once we know how to use structures, we can improve on this even more. So during the next lecture next week, we can revisit our simple test project and improve on it. But for now, this is, and for the assignment as said, which you had with the website and the dissection and construction of floating point numbers, such an approach is pretty good. The only difference, of course, will be that you will have like one input field for floats and another input field for integers. No, will you? No. The assignment is made out of two things. First of all, dissect floats to to the component. So we will have one float array and 3 arrays of integers with outputs, and then your test will need to have like this, and the next one and the next one, so on. And for the second part of the assignment, you will have 3 input arrays of integers and 1 output array of floats. And for each of them, you will have, I mean, we can write it down. So so you will have float my in 1 is equals 1 to 3.4, comma 567.8, let's say, and then you will have int or char is enough, sign my sign1 equals, or just my sign, you could do it my float, my floats, my signs, and there would be something in here that you have to fill in. Then my exponents I think will be int. I don't think, I'm not sure if that will fit in the char. And of course the mantissa will definitely be int. And then you have your pool my results or my test. Oops, my test. And this of course needs to be all right here as well. And for the B case, the opposite, you will have your signs, and then you will have your floats, and then you will have again this. Actually, since this kind of it will be basically the same ones. You can use the same ones because you just want to test the conversion in both ways. So you write down the associations, and then you make one loop that tests converting from the float to those 3, and then you make another loop which tests converting from the same 3 to the float. So yeah, you really don't even need the. I like 2 different cases. You will just have tests 1 and tests 2. Test 2 will be for the opposite direction of the conversion. Okay, so are there any questions with regard to the homework and the unit tests that you have to implement? No questions? Okay, so since there are no more questions and we are close to the end time anyways, there's a question: is it okay to type the targeted numbers in the consulting? I don't understand the question. What do you mean with in the consulting? Yes, you need to write the tests for the assignment 2 as well. So basically for all homeworks, your submission should look like you have some main function that in the end has this result arrays with the tests, so that it's easy. I just have to run the project and then I can see whether the tests are passed, and then I will of course take a look whether it's plausible. So just making pre-filling it with true and not doing anything else will of course not work, but it is very helpful to see that the code really does what it's supposed to do. And what was assignment 2? It was something, yeah, for the loop. How we do that? The loop is, I mean, for the loop what the loop basically does in the end, it modifies those 2 values. So once the loop have run, these 2 values will have something. We can run it quickly to see what we will end up with. So var1 is equals 153, and var2 2 is equals just copy that. Is equals this. So your test could be as simple as just checking whether those two values are the same, whether they didn't change. Because if you would change something in the loop here, let's say this would be 5, or the loop would break early, then of course the values are not correct. Or let's make another example. Because this you rather wanted. Let's say, actually I don't know whether we hit this case. We don't hit this case. I would like to hit this case. Then let's run it. I'll show you one more thing. You can here condition and then write a condition. So let's say I want I to be equals 9. And then the breakpoint will only break if the condition is met. So now if I run it again, once we are here, it's I is already 9. And then let's see what this is. So this is 152. So I will make the code here that it will break at 152, so that the last go through, the iterator, the thing here will not be touched. So we need to update this. Okay, now we have touched all the code paths. I will also check whether we are touching those code paths. Okay, we are touching this one, and we are touching this one. Yeah, so we are touching all of them. This is good. And now let's say that you did something, and for some reason this code here, this code path here would never be taken. Then the result will be of course wrong, because it will be one too much. So this way you can to some extent test that everything works as expected. So you should specify all of the test values inside your program. The program should not ask the user to enter a number or something like that. It should just come with a list of preset numbers for testing, and then do tests, and then have the result array with tests passed or tests failed. There is no need to make like user input or anything, especially that we have not talked about how to do such things. Okay, there is another question. Someone is using Mac OS. How we do that? If you can compile it on Mac OS, if you can compile a main CPP which only includes the standard C library, then you can just submit the CPP file, the main CPP file, without the rest of the Visual Studio project. This is fine. Any more questions? Okay, so if someone already submitted something that takes a user input, this is fine. You don't need to rewrite your submission to use this style of unit tests. But use those unit tests in future. Also, what you could do is, if you really want to have user input, you can write first like some unit tests, right? So then the program writes internal tests passed, and then it writes please enter number, so that you can have both things, and the user also can be sure that the program passed its own internal self-tests. Good. Any other questions? No questions? Okay. Then, if there are no other questions, then we will finish the lecture at this point. As said, the subject for the next lecture will be structures. And since structures are not super long, I think we will, during the next lecture, also take a look at functions. Functions might be longer, so maybe it will break into the next lecture, the over next lecture, and so on. Okay, so have a nice Friday and a nice weekend. See you next week. Bye bye.